Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're going to do a quick review of half reactions. So pause the video, work through this, and then we'll go back through this. If there's any questions with anything, remember lts.pd@gmail.com. Like, share, subscribe. Any questions, let me know. All right, here we go. Okay, first thing we do is put the reaction, iodide to iodate, and dichromate to chromium 3+ ions. Check, we're going to need to put a 2 in front of the chromium to balance that out. Iodines are fine. Balancing our oxygens, we're going to assume that it's acidic. So therefore, we're just going to add the hydrogen ions, a simpler one. Add 3 waters for the iodate, and then 6 hydrogens to balance that out. We're going to add, and the electrons there. So we're going to have 6 electrons to balance it out. Negative, 6+ to balance it out, 6-. All right, then for the over here, we have to add 7 waters because of the hydrogens. That means we're going to add 14 hydrogens. Then we have 14 minus 2, that's plus 12. So we have to add 6 over here. Awesome, because they're already equal. Nothing can have to be multiplied. Put them underneath each other. The electrons cross out. We're going to lose all the hydrogen ions on the product side, 8 left on the reactant side. Water is going to lose all the waters on the reactant side, 4 waters left on the product side. Add them up, we end up with 8 H pluses plus Cr2O7 2- plus iodide I- goes to IO3- plus 2 Cr3 plus 4 waters. Checking our charges, get plus 5 plus 8 minus 3, that's plus 5. And then over here, minus 1 plus 6, so that's also going to be plus 5. Remember, this isn't the answer. This is just a check to see if you did it right. All right, awesome. Now today, we're going to look at a new concept. It's called the EMF. When we talked about the voltaic cell, we talked about the voltage that's being produced. The EMF is the way that we generate the voltage. EMF is defined as the electromotive force. That's what it stands for. And it's the potential difference between 2 electrodes produces the driving force that pushes the electrons, that generates the voltage. Now, in order to do that, I need this chart right here, which is the standard reduction potentials. And what that's going to do for us is it's going to give us all the values that we need for the given reductions to help us generate the correct values. All right, so this chart right here is what we're looking at. All right, and that's going to give it 2 in the units of voltage. Now, when we do this, it's going to be find the standard reduction potentials, which we have right here, and we take the standard reduction potential for the cathode. Remember, cathode is reduction. It's gaining electrons, and that's the way these are all written. Subtract the reduction potential for the anode, which is the oxidation, which is losing. It's basically mean the negative of this value, and we get the standard, the EMF for the reaction. All right, so let's take this one right here. We have copper 2+ plus zinc gives us copper plus zinc ion. We split that into 2 parts. So zinc goes to zinc plus 2, and copper plus 2 goes to copper. Now, when we look over here, we know 2 electrons there and 2 electrons there. So we're going to be, this is my oxidation because I'm losing electrons, and this is my reduction because it's gaining electrons. We look at our standard reduction potential expression for the EMF. So we look at our chart over here, and we see that for copper to copper 2+, it's 0.34. And for zinc to zinc plus, all the way down here, where's it at? Zinc. If you look inside of there, yeah, that's in there. You get negative 0.76. Now, when you do this, if you get a negative number, what that means is you just mess them up. So just switch the numbers. You can't get a negative value. It's always going to be positive. So we take 0.34 volts minus a minus 0.76 volts. And we end up with 1.10 volts for the standard reduction potential for the EMF of that reaction. All right, let's try another one. This time we're going to take dichromate ion plus iodine ion gives me chromium 3 plus iodide. Okay, we split the reactions, and there we go. Now you can see these aren't balanced this time, but we don't care about that. All we use is the value off of this chart. So when you look to this chart, I will pull this up, make this bigger later. All right, we end up with that. This is my reduction because I'm gaining. This is my oxidation because I'm losing. So that's my cathode, that's my anode. Our reduction potentials from the chart, if you look through it, you'll see that's 1.33 volts. If you look through it over here, it's 0.536 volts. So we take 1.33 minus 0.56, and we add a 0.76 volts. That's my EMF. All right, hopefully that's not too bad. That's pretty simple. Now, the next thing we'll look at is called Gibbs free energy. We discussed Gibbs free energy. We talked about thermochemistry. The Gibbs free energy then and is still the measure of spontaneity of reaction. Now, we can use EMF to determine the spontaneity of reaction. The equation now is slightly different, though. It's still delta G, but delta G is now equal to negative NFE, where N is the number of moles of electrons. F is called the Faraday constant, 96,500 joules per mole. And E is the electromotive force standard that we found just before. So let's take a look at a problem here. I want to know what the Gibbs free energy for the fluorine-oxygen reactions. We got to go back over here. Fluorine's right here, and oxygen right down here. So the reactions, using that chart, we end up with fluorine and oxygen, okay? Now, this is my reduction because this one's gaining. This is my oxidation because it's losing. So we're going to take 2.87 volts and 1.23 volts, plug them in equation, we get 1.64 volts. That's my E prime, that's my EMF standard. All right, now, using our equation for Gibbs free energy, delta G is equal to negative NFE. If I'm losing 2 and gaining 4, the number is going to be 4, so I'm losing 4 electrons. My Faraday constant is always the same, 96,500 joules per mole volt. And my voltage we just found, the EMF, is going to be 1.64 volts. My volts cross out. When you get that, we get 3 sig figs of 1.64. So we get negative 633,000 joules per mole. But remember, we don't ever use joules, we use kilojoules, divide by 1,000. So the answer there is negative 633 kilojoules per mole. Hopefully not too bad. All right, now let's try another one. This time silver and tin. All right, let's try to make this a little bigger for you so that way you can see it big. If you want to take a screenshot of it, help yourself out. All right, great. Okay, so let's try and get back down now. All right, so that being the case, here we go. So there, using that chart, tin is that reaction. It's a negative 0.14 volt. Silver is that reaction. It's 1.99 volts. So this has got to be my cathode, and this has to be my anode in order to get a positive value. So we end up with a total of 2.13 volts. That's my E prime, my EMF standard. All right, so for Gibbs is delta negative NFE prime. So N is 2 because we're gaining 2 and losing 1, but it's going to be 2 going to multiply. All right, so we're going to take 96,500 joule volt and my 2.315, plug them in. Volts are going to cross out. We're going to get negative 411,000 joules per mole, divide by 1,000. We're going to get negative 411 kilojoules per mole. That's my spontaneity reaction. This is a spontaneous reaction. Because remember, if it's negative, it's a spontaneous reaction. Okay, one more. This time, do it on your own. I want silver to nickel. So take your time, work through this. Any questions, let me know. All right, here we go. There's all the work. Final answer is negative 208.2 kilojoules per mole. All right, not too bad. Hopefully you got it. Take care. God bless. Bye.